In the last part of discussion, we'll develop the equation for angle of twist that equal to theta. Already we have developed the equation for the shear strain and the shear stress, which one is a function of radius r. So shear strain is given as maximum value of the shear strain multiplied by r divided by the total radius equal to capital R. Similarly, the shear stress at any radius r is maximum shear stress multiplied by r divided by j, and the maximum shear stress is simply given as product of torque multiplied by r divided by j. And because of a elastic in nature, the modulus of this T can be equal to tau max divided by the maximum shear strain. So we'll consider here a shaft of length equal to r, radius equal to capital R is subjected to torque T. Here, due to the application of a torque, the point A will move from A to B, and because of this, we have a angular deformation that equal to theta. So this angular deformation AB is given as a sector length. So this value of theta is very small. So we can use the value of theta in radian multiplied by radius r. Whereas if we use the maximum shear strain, which is given as the gamma max on the outer surface, same distance AB we can also write as the maximum shear strain gamma max multiplied by the distance L, that is the length of shaft. So from these two equations we can write the value of theta is equal to gamma maximum, that is the maximum shear strain multiplied by length divided by the radius r. Since here the g is equal to tau max upon gamma max, so gamma max will be equal to tau max by g. So we can replace the value of gamma max here using tau max by modulus of dt. So we have theta equal to tau max, that is the maximum shear stress, multiplied by L divided by g multiplied by r. The maximum shear stress is also equal to T multiplied by R by J. So let's substitute for tau max. In that case, we'll get theta, that is the angle of twist, equal to T multiplied by R divided by J is further multiplied by L divided by G into R. So R value will be get cancelled here. It means that the theta is independent of R. So whatever the radius we have on the cross section area, value of theta is remains same. Secondly, we get here the value of theta is equal to T multiplied by L divided by J multiplied by G. So angle of twist is dependent on the torque. Torque will be higher, the value of theta will be higher. It depends upon the length. For a larger shaft length, we have higher value of theta. For a smaller diameter, J will be smaller and theta will be higher. For higher diameter, theta will be smaller and inversely proportional to modulus of rigidity. Value of E into I, that is the product of E into I, is called as flexural rigidity. Similarly, the product of G into J is called as torsional rigidity. And if you recall the axial loading, in that case we have the deformation is given as dl is same as equal to F into L divided by area divided by Young modulus. Almost symmetrical formula here. We have a torque here. In this case, we have F. J and A both are geometric property. G and E both are material property. So almost analogous to the axial loading, we have to solve the problem of torsion. So finally, we collect here all the formula for torsion. So the torsion formula is given as T by J is equal to tau divided by radius r. This, when we write here radius r, that means that you treat the value of tau equal to the maximum shear stress and is same as equal to G multiplied by theta divided by L, where G is called as the modulus of shear, theta is the angle of twist, that is the angular twist at a distance equal to L, and T is the applied torque. J value is given as for solid shaft equal to pi by 32 d to the power 4, and for solid shaft the quick formula we can remember to calculate the torque is equal to pi by 16 multiplied by dq multiplied by the maximum value of the shear stress. And in the case of the hollow shaft, we have polar moment of inertia is given as pi by 32 do to the power 4 minus di to the power 4. Do represents the outer diameter, di represents the inner diameter, and for hollow shaft our quick formula is torque equal to pi by 16 multiplied by do cube into 1 minus k to the power 4 multiplied by the maximum shear stress, where the constant k will be equal to di divided by do. So this quick formula will work in the case of solid and the hollow shaft. Otherwise we can use this formula for finding the any unknown. The flexure formula and the torsion formula, they are almost symmetrical. Instead of torque we have to use the bending moment equal to m. Instead of J, we have to use the moment of inertia equal to I. Instead of tau, we have to use the bending stress equal to sigma b. Instead of radius r, it will be equal to the distance y. And on the right hand side, we have E divided by r. So almost symmetrical torsion and the flexure formula. In the bending moment, we have introduced the term that is called as section modulus, and section modulus is defined as the moment of inertia or the second moment of area divided by the distance y, which is represented by z. Similar to this, we can define here the polar section modulus, which one is represented by zp, is same as equal to the polar moment of inertia divided by the radius r. Now we can take advantage of the polar section modulus zp in the equation of finding the value of tau max. If you find here the value of the tau max, that is the maximum shear, is given as torque multiplied by r divided by j, which can be rewritten as j by r. So we have tau max, that is the maximum value of a shear stress when subjected to torque equal to T, is T multiplied by r divided by j. So this value of r we can write in denominator. So we will get the maximum value of the shear stress equal to torque divided by the polar moment of inertia j divided by radius r, and this value of j by r we can replace as the polar section modulus. So we have tau max, that is the maximum shear stress due to the torque T, is divided by j by r, is same as the polar section modulus. This equation we can use for comparing the two sections for two different diameters or two hollow sections for two different inner and outer diameter. So here we'll get torque will be equals to the maximum value of the shear stress multiplied by the polar section modulus. From this equation we can conclude here the maximum shear stress in a torsion member is inversely proportional to polar section modulus. It means that if the value of Zp will increase, then the value of tau max will decrease. So you have to select the value of section modulus should be higher. In that case the shear stress will be smaller and it will be lower value as compared to SYS. In that case our design is a safe design. Almost we are done. So this one is a abstract, you have to remember. So quick formula is torque is equal to pi by 16 d cube into tau max for solid shaft. In the hollow shaft we have torque is equal to pi by 16 do cube into 1 minus k to the power tau max, where k will be equal to di by do. This one is a generalized formula you can remember to find the value of theta, where theta will be equal to t multiplied by l divided by j into g. And this formula you can use for comparison of two sections. So we'll take here some elementary numerical which are commonly asked in the GATE examination. Very basic numericals. And then in the next video we'll start with the torsion member in series and in parallel, and we'll classify that problem into two categories. One is the statically determinate and statically indeterminate problems. A solid circular shaft of 60 mm diameter transmits a torque of 600 Newton meter. The value of the maximum shear stress we have to find out. These questions you can manage in 2 minutes, so I will directly solve this question. Just remember here we have solid circular shaft. So for solid circular shaft, torque is given as pi by 16 into d cube multiplied by maximum value of the shear stress. Torque is given as 600 Newton meter. Torque you have to always take in Newton mm. So we have 600 into 10 to the power 3 equal to pi by 16 and we have diameter D is equal to 60 cube of it multiplied by the value of shear stress that equal to tau max. So we'll get the value of maximum shear in the case of pure torsion is close to 37.72 megapascal. Just based on direct formula, choice A is correct. A cylindrical rod of diameter equal to 10 mm, length equal to 1 mm fixed at one end. The other end is twisted by an angle equal to 10 degree. You have to always use radian by applying a torque. The maximum shear strain is given as P into 10 to the power minus 3. Then the value of P is equal to, you have to find out. We have given the diameter equal to 10 mm, length equal to 1 meter, theta equal to 10 degree is same as equal to 10 multiplied by pi divided by 180. That is equal to pi divided by 18. So you have to always use theta in radian. The maximum shear strain you have to find out in terms of P and is given as P into 10 to the power minus 3. Now recall that the maximum shear strain gamma max is same as equal to tau max divided by modulus of GT G. So this formula you have to develop first. Now we have torsion formula is given as torque divided by the polar moment of inertia J is equal to the maximum value of the shear stress tau max divided by the radius R is equal to G multiplied by theta divided by L. So we can rearrange this term as tau max by G, which will be equal to theta multiplied by R divided by L. So the maximum value of the shear strain is tau max divided by G. From the last two terms we can develop the equation for tau max by G is equal to theta multiplied by radius R divided by length L. Take care that theta must be in radian. That equal to pi divided by 18 multiplied by radius R, which will be equal to 5 mm, and we have to take the length is also in mm, that is divided by 1000. So this answer is close to 0.8726 into 10 to the power minus 3. And in the question he says that the maximum shear strain is P into 10 to the power minus 3. So we can compare these two results and we get the value of P is close to 0.8726. It is required to replace a solid shaft of diameter equal to 45 mm with a hollow shaft of external diameter equal to 50. For the same constant torque and the same maximum shear stress, the internal diameter of the hollow shaft you have to find out. So for solid shaft we have given the diameter D is equal to 45 mm, and for hollow shaft the external diameter DO is given as 50 mm, and we need to calculate the internal diameter DI. For both shaft our torque is remains same, even the value of tau max is also remains same. So there is no change in the shear stress and the torque. So just we'll compare here the solid shaft torque and the hollow shaft torque. In the case of solid shaft, the torque is given as pi by 16 d cube into tau max, and for hollow shaft it is given as pi by 16 do cube into 1 minus k to the power 4 multiplied by t max, where value of k will be equal to di by do. So if you take a ratio here, the torque will be get cancelled, pi by 16 will be cancelled, tau max will be cancelled. In that case we left here with d cube, which is equal to do cube into 1 minus k to the power 4. So once we know the value of k, we can calculate the value of di. We have d cube is same as equal to 45 cube, do cube is equal to 50 cube, 1 minus k to the power 4. So this was the result obtained by dividing 1 with 2, or we can equate them. Solve this, we will get the value of k. The constant k will be come out to be 0.72. and this constant K is same as equal to di divided by do. So we have di is equal to 0.72 times do, which is equal to 50. So internal diameter for the hollow shaft come out to be 36.05 mm. Very basic numericals they ask you for 1 mark or 2 marks. A hollow shaft is subjected to torsion. The shear stress variation shaft along the radius is given. We have a linear distribution of a shear stress. So first figure is wrong. This one is non-linear. This one is also wrong. And at the inner radius, the shear stress is not 0. Rather, this distribution is correct. So we have maximum value of a shear stress at the outer radius, that equal to tau max. At inner radius, we have a certain value, that equal to tau 1. So choice C is correct choice. The maximum and the minimum shear stress in a hollow circular shaft of outer diameter 20 and thickness 2 mm subjected to torque of 92.7 Newton meter will be, you have to calculate both maximum and the minimum. Maximum will occur at outer radius, minimum will occur at inner radius. We have given here the outer diameter equal to 20, so minus 2 times of thickness will give you inner diameter. And we have given a torque. So using torque, first of all we have to find out the value of the maximum shear stress which will occur on the outer radius. So let's represent here a hollow shaft and the shear stress distribution. On the outer radius we have tau 2 is equal to tau max. That tau max we can calculate from this equation. We have inner diameter equal to d1, outer diameter equal to d2. This value of d2 is equal to 20 mm. And we have given the value of thickness, that is this value of thickness equal to 2 mm. From this we can calculate the inner diameter d1. So we have inner diameter d1 is equal to d2 minus 2 times thickness. We have outer diameter equal to 20 minus 2 times the thickness equal to 2. That is 20 minus 4 is equal to 16 mm. In this equation we are going to use the K value. K is same as equal to di divided by do, which is same as the inner diameter d1 divided by outer diameter d2. d1 is equal to 16 and we have d2 is equal to 20. 16 by 20, so value of K will be equal to 0.8. For hollow shaft we have torque is equal to pi by 16 do cube into 1 minus K to the power 4 into maximum shear. The torque is given as 92.7, so you have to use this torque in Newton mm. So we have 92.7 into 10 to the power 3 is equal to pi by 16. Outer diameter is known, that equal to 20, cube of it into 1 minus K. K is equal to 0.8. So we have 0.8 to the power 4 multiplied by tau max. So the maximum shear stress will occur on the outer radius R2 will be equal to exactly 100 megapascal. And since we have a linear distribution here, we can write tau 1 at radius R1 is equal to tau max at radius equal to R2. So the minimum value of the shear stress is tau 1 is tau max equal to 100. R1 is equal to 16 by 2. So we have 16 by 2. R2 is equal to 20 by 2. That is same as equal to 0.8. So 0.8 into 100, that equal to 80 megapascal. So maximum is 100 and the minimum is 80. Our choice B. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.